So we'll be looking at what's happening inside the HPLC column and how we get separation occurring with normal phase, reverse phase, and a sort of modified version of reverse phase for analysing chiral compounds. I'm probably going to have to leave the ion exchange and size exclusion chromatography to a later session. I'll see how I get on with the timing. I haven't bothered printing out the notes for that yet, but if it looks like I'll manage that, I'll go and print off some extra slides. But just kind of going back over what I covered earlier, there's these various different modes of chromatography, different types of stationary phase, relying on different physical and chemical properties for separation, and we'll be looking at this evening a little bit about adsorption, so that's what's referred to as normal phase HPLC, partitioning effects, that comes into the so-called bonded phase or reverse phase HPLC. With size exclusion, just very briefly, it's to do with size differences of molecules and how they move in and out of small pores in the stationary phase. Ion exchange is also to do with ionic interactions with the stationary phase. And I'm not really going to say any more about the affinity chromatography, which is based on very specific ligand receptor interactions, things like antibody-antigen interactions. So I'm going to start off with the normal phase HPLC. The name comes about because it was the first technique which was developed. So it was originally the standard method. It's not used that often anymore, but there's probably still applications where it gives good results and it's worth trying out. The material's a bit cheaper than the more commonly used reverse phase HPLC. And what you have is columns packed with polar materials like mostly silica, but it can also be alumina, aluminium oxide. And the point is with these is that they have a polar surface to them with lots of hydroxyl groups presented. And because it's a polar stationary phase, and in contrast to that, you use a non-polar mobile phase. So it's something that's very non-polar, like hexane or chloroform, but then that's mixed in with a small amount of a significantly more polar solvent, like isopropanol. And I'll talk later on about what the role of that polar solvent is. And the way that you distinguish different molecules is that they have different degrees of polarity, different numbers of dipolar groups, hydrogen bonding groups, etc. And they will adsorb to the surface of the stationary phase with different binding strengths. So the more polar the molecule is, the stronger it's going to bind to the surface, so the longer it takes for it to come through the column. What I'm also going to be discussing is the sort of general idea of bonded phase HPLC, and this is where you chemically modify the surface of the silica, and it gives you a much greater variety of different materials, depending on what modification you make. But it's mostly done with hydrocarbon chains, and most commonly an 18-carbon chain, and that's referred to as octadecyl silica, or ODS, and that's referred to as reverse phase HPLC, because now we've turned the stationary phase into a non-polar material, and we use a polar solvent as the mobile phase. And this is a bit more complicated because you can have some kind of adsorption processes due to, it would be mainly van der Waals interactions with the hydrocarbon surface, but you can also get the molecules that kind of, you can think about the bonded molecules as like a very thin layer of liquid. So the molecules are kind of partially dissolving in that bonded layer of hydrocarbons. So you can think about it as a partitioning process between the polar mobile phase and the non-polar stationary phase liquid. So I'll come back to discuss those in a bit more detail, but first of all, we're kind of sort of starting from the outside and kind of moving in to think about what's happening inside the column. But first of all, we'll think about the columns themselves. So I'll start sort of, I mean, you've seen the column in the practical class, but you can have a sort of closer look at it if you're not familiar with them. So, you know, they're quite, well, I don't know, if you like sort of mechanical things and tools and so on, they're quite nice objects in themselves, like nice sort of solid, shiny things. The stainless steel is essential because of the high pressures that build up during the HPLC process. So it needs to be very mechanically strong. And I think I sort of talked about this before, but you know, the inside they're lined with a cylinder of glass, and that's because the metal surfaces could catalyze reactions within the mobile phase and offer potential binding sites for particular types of molecule, so that can interfere with the process and give side reactions and tailing of peaks and so on. So we have this inert glass surface which prevents these things happening. You usually need some extra components on the column. So I've talked about how I think I mentioned how you need to remove insoluble material. Ideally, you would do that before you put the mobile phase in by filtering it. But in case any dust gets into the system, ideally you would have just a little filter device before the column, just with sort of very fine pores in the filter. And in addition, you'd also use a guard column, and this is just a very short column with the same stationary phase as so you have a very short column, and the point of this is if you've got something going into the system which will interact very strongly with the stationary phase, it can get stuck there. So it basically just takes far too long for it to elute from the column, and it blocks binding sites, and if there's enough material, it can sort of close up the space between the stationary phase particles, making it harder to push the mobile phase through, building up too much pressure. I suspect that's what's going on with the system that we did the lab class on. I think the first thing I'm going to need to try to do to solve that is to just replace the guard column. But I think we've run out of spare guard columns, so we need to order some more in. But the point of having that is that you can just, if it gets blocked and the pressure is getting too high, you just throw away the guard column, put a new one in, and it's relatively cheap compared to wrecking your more expensive full-size column. The guard columns, they're usually, we haven't got one attached to that sort of little column I passed around, but they're usually just a few millimeters long. So there's not going to be any separation occurring on the guard column. It's just there as a sort of trap for any very sticky materials. So that actually, pass around some other columns, but this is sort of more like the one that we did the class sessions on. So this is a standard size of column that I'm passing around now, referred to as analytical columns. The cylinder that the mobile phase, the stationary phase is packed into is 4.6 millimeter diameter. And it can be a range of lengths, 5 to 25 centimeters commonly. And the particles inside, they're mostly nowadays probably 5 micron diameter, but it can vary. Older columns would maybe have 10 micron. And typically the kind of flow rate that you can achieve without getting too much pressure is 1 milliliter per minute. And the capacity of the column for sample binding is about 50 micrograms. So it's not really enough to do much with afterwards. It's hard to collect the separated material and do additional experiments with it. Hence referred to as analytical rather than preparative. I don't have an example of a semi-prep column. We might have one somewhere in the lab, but I've never used it. There's a bigger inside. We've got 1 centimeter internal diameter, 25 centimeters long. They may have larger particles within because you've got sort of much bigger, larger amount of stationary phase, a lot of stuff for the mobile phase to get through. So it takes a bit more sort of pressure to push it through. But you can put in about 10 milligrams per run the injection. So that is now a useful amount of material that can be purified using these columns. Needs higher flow rate to achieve good separation, so it's usually about 2 milliliter per minute. I do have the sort of next size up. This is the preparative column. Take care with this. It costs about £2,000 to £3,000 for one of these. So this allows you to purify up to about 100 milligrams of material. So that's now a very useful quantity. You can do lots of further experiments with that. If it's a potential drug compound, you can do lots of bioassays with that quantity. That would usually be sort of 10 micron diameter particles and a flow rate of about 10 milliliter per minute to give the optimum separation. You can get even bigger ones in industrial labs mostly. Can't remember what the biggest one I've come across is. You can get them that are like maybe sort of 10 to 20 centimeters diameter inside, and you're sort of getting up to being able to purify gram quantities of material. That's the kind of thing that'd be used in a pharmaceutical company to build up enough material for preclinical testing, but then for actual manufacturing, you would have to find other ways of purifying the material. There's a limit to the size that you can really do chromatography on. And the first column that I sent around was the small one. That's what's referred to as microbore column, and that uses smaller diameter particles, 2 or 3 micron diameter, with sort of 1 or 2 millimeter diameter inside. So this, if you go through the theoretical analysis, you can kind of find a justification for why this allows lower flow rates to occur, but without losing the separation efficiency. So you can bring the flow rate down to 200 microliters per minute if it's a 2 millimeter column, or even lower than that, 50 microliter per minute for the 1 millimeter diameter columns. And obviously this saves on using so much solvent, makes it cheaper, less sort of environmentally damaging, and I won't sort of dwell on this too much, but yeah, it allows you to inject it directly into a mass spectrometry detector, because the mass spectrometer can only cope with so much liquid going in, because it has to be vaporized before it goes into where the ions are analyzed. If the flow rate's too high, then the vacuum system can't cope with that amount of liquid going in. But because of the low volumes involved, you have to reduce the size of the tubing and things like the detector flow cell, so that you minimize the amount of diffusion leading to peak broadening in the chromatograph. And another thing, I've never actually seen one of these in person, but I don't think it's really caught on so much, especially since UPLC was developed, which I've sort of discussed previously. But for a while, there was a trend for developing capillary columns. So this is, we'll come back to this with gas chromatography, but what this means is that the stationary phase is not in the form of small particles which are packed into the column. It's coated on the inside of any narrow capillary. So you have a kind of open space in the middle of the capillary that the mobile phase passes down, and the sample molecules are interacting with the walls of the capillary as they pass through it. And so the internal diameter of these capillaries would be much less than a millimeter, 150 or 75 micrometers, and the kind of flow rates for the mobile phase, so the liquids are going through the middle of this capillary, just a few microliters per minute or less. But this requires specific pumps to be able to control those low flow rates precisely and give you reproducible results. And it's going to affect the detectors as well, because of the much lower volumes that are going through into the detectors. Okay, so now sort of thinking a bit more about the stationary phase materials themselves. So normal phase, but it also applies to the bonded phase material. You have to think about the silica materials that are being used. And it's referred to as microparticulate silica because it's particles that are just a few microns in diameter. So mostly silica, sometimes alumina, rarely I think graphite maybe. For normal phase chromatography. For bonded phase, it would be chemically modified silica. We'll come back to that later on. Just sort of having a quick look at some of the other types of chromatography. If you're doing ion exchange or size exclusion, polystyrene can also be used as the underlying material, because it's it's a relatively sort of inert material for non-covalent binding. It's just it's basically a hydrocarbon, so there's no hydrogen bonding or dipolar interactions. So you can use it for size exclusion, where we want the separation just to be on the size, not the polarity of the molecules. And for ion exchange, it's got advantages that it's easy to do chemical reactions to modify the benzene rings which you find in polystyrene to add negatively or positively charged groups. You can also use polysaccharides for well, both size exclusion and ion exchange chromatography. They're, this really mostly comes about, I think, for protein separations, where you want quite large pore sizes for the large protein molecules to move in and out of. You can also do chemical modification of the carbohydrate groups in the polysaccharides to add charged groups for ion exchange. But we'll sort of be focusing mainly now on silica as the material. So when HPLC was developed in the 1960s, the manufacturing processes available could only really produce relatively large particles, 20 to 40 microns. And these, so you want to maximize the surface area to get a good efficient separation, and so that's one problem with these, because they, large particles that are packed together will give you a relatively low amount of surface area per mass of the silica. But an additional problem is shown on the diagram here. They're not solid, completely solid materials. They are sort of a bit porous. So there's these little channels going through the middle of the silica particles, which is unavoidable. And what can happen is you can get the mobile phase slowly diffusing in and out of these channels. So there's a certain proportion of the mobile phase, and hence your sample molecules are slowly diffusing in and out of these pores, and that's going to increase the effect of diffusion on broadening the peaks in your chromatogram. So these relatively large particles give you relatively poor resolution at quite broad peaks. This is just for historical interest. This is not sort of relevant to current applications, but one solution, but it kind of illustrates what the problems that we're trying to solve here. One solution was to have little metal, solid metal particles, which are then coated with the silica. So it gives you, the same kind of surface area of the silica, but these pores are much shorter now because they don't sort of go into the metal core. Or well, like a glass bead with a metal particle. Then the sort of better solution was to find, I'm not sure what exactly how they achieved this, but better manufacturing processes which give you smaller particles. Down from sort of 20 microns to 5 microns or less. And one thing, we're increasing the overall surface area of the silica for the same mass of the material. And we're also reducing the size of these pores, so it reduces this extra diffusion process, which gives rise to broadening of the peaks. Just to sort of give an idea of what the material is like, so it's the overall formula is SiO4, but that's made up of this sort of complex 3D network of silicon-oxygen chains. It's all very highly cross-linked with these. Each silicon is attached to 4 oxygen atoms. Each oxygen atom attached to 2 silicon atoms, and you've got sort of chains sort of intersecting and sort of branching off in all directions, giving you this dense 3-dimensional network of these chains. But we have to think about what happens at the surface. So at some point, it's not an infinite chain. So when it gets to the surface, what happens is it stops at an oxygen atom, which then becomes attached to a hydrogen atom. So we have these polar OH groups presented at the surface, which can take part in dipolar interactions and hydrogen bonding. They're also slightly acidic. I can't remember what the pKa value is, but you can get a bit of dissociation to form O- groups at low pH. Sorry, a high pH. And just a brief run through the chemical synthesis of these materials. There's a couple of ways that you can do this, which gives rise to different shapes of particles, which can affect the separation efficiency for different mixtures. This is something I'll comment on later on. But just very, there's going to be sort of lots and lots of, many different manufacturing processes that the details of exactly how it's done. But very roughly, there's these two different approaches which can give different general shapes of the silica particles. So called angular silica, this is where you've got, it's more kind of like a little crystals with edges and corners and so on. And that can be done by taking sodium silicate and acidifying the solution and letting the silicate ions react together with the acid to form, to start to nucleate the formation of these silica crystals. I won't go through the whole, lots of the mechanism of the process, but what you have to imagine is, one of these OH groups on the silicate. If that gets protonated, then you've got an H2O group attached to the silicon, and that can easily be removed to release a water molecule. And it can be replaced with the negatively charged oxygen on another silicate ion to form a link between two silicon atoms. And that process just keeps on occurring, growing the silicon oxygen chains until you get a particle that's a few microns in diameter. You can get a different shape of the particle. It's more spherical, and that is done by constraining the reaction within a very small volume. So what you can do this as an emulsion. So you'll have the reacting solution dispersed within another liquid in very small bubbles of the reacting solution. Just a few microns across, or you can do it as a spray, so the reacting solution is dispersed in air, forming sort of very small droplets, just a few microns in diameter, and within these droplets you've got the reaction occurring to form the silica, but it can only occur up to a certain size depending on the size of the droplets that you've managed to create. Chemistry is a bit different, so you start off with this tetraethyl silicate ion. No, it's not an ion. It's like you take the SiO4 group, attach 4 ethyl groups to it, so you've got this neutral molecule. If you react that under alkaline condition, what happens, the sodium, the hydroxide ion will replace one of these O ethyl groups, so you end up with an OH group, and then that OH group can be deprotonated to give O-. That oxygen atom can then react with another molecule of the tetraethoxysilane to replace another O ethyl group, So you've now joined two of them together. I'll sort of give a quick sketch of the intermediate that would form. So that'd be your first intermediate, and then you can just repeat the process. So another molecule of this would react with the hydroxide and come in and replace the lethal groups, and so on. So the precise setup of the reaction can give you slightly different morphology for the silica particles. Just depend, it's going to depend on the shape and size of the reaction vessel that you use. So this is getting into like chemical engineering processes. And what we'll see later on is that different manufacturers, even if it's like nominally the same material, you can get different results coming out, and it's all down to the sort of fine detail of exactly the shape of the particles and exactly how they pack into the column. Because these are polymerization processes, although on this side of the column it will say like 5 micron diameter, this will be a range around that value. That's going to be the average value. So there's going to be a sort of slight range of different size particles coming together. And just some numbers here. They still have pores within them, with a few nanometers in diameter, and you end up with quite a high overall surface area, hundreds of meters squared per gram of material. Okay, so now think about the details of what's happening when your sample molecules pass across the stationary phase and start to interact. I'm just doing this in a very non-quantitative fashion from now on. So the original method involving adsorption to the surface of the stationary phase, so it's referred to as normal phase HPLC. And mostly silica, sometimes alumina, graphite, but we've got the sample molecules. They come through the mobile phase, they pass across the silica surface, they can interact with the OH groups if they have polar bonds or hydrogen bonding groups, and so you get this equilibrium set up between being dissolved in the mobile phase and being absorbed onto the silica surface. Different molecules will have different polarities and therefore different adsorption strengths. So they're for different molecules will have a different equilibrium for how much time they spend attached to the stationary phase. So relatively simple concept, and I'm not going to get into the quantitative modelling about exactly how this happens. But just some practical aspects. So when the silica is manufactured, it comes out of an aqueous solution, and it is going to have a layer of water molecules bound to the surface by hydrogen bonds. And that's going to kind of not exactly block, but reduce the interaction that your sample molecules can have with the surface. So in order to minimize this effect, we have to get rid of the water molecules. So we have to activate the material by heating, just to sort of, evaporate off the water molecules. I'm not sure if this occurs before or after we pack it into the column. this occurs during the manufacturing process, and then you would need to fill up the column with a non-polar solvent to prevent water getting in and sticking to the surface again. So, we're mostly using a non-polar solvent so that we have this, strong difference between the mobile phase and the non-polar mobile phase and the polar silica surface. But we use a small amount of a polar solvent as well. And the idea here is that this competes with your sample molecules for binding to the silica surface. So it helps to move your sample molecules along. So it displaces them from the silica surface so they can get pushed back into the mobile phase. They can move along a little bit further before they stick back to the silica surface. So you get this constant competing equilibria of the sample molecules bound to the silica or the polar solvent molecules bound to the silica. And it allows you to change the rate of elution of your molecules by changing the amount of the polar solvent. So if you increase the amount of the polar solvent, then there's more competition for binding to the silica. So that's going to accelerate the elution of your sample molecules. But this process of reaching an equilibrium between being bound to the surface and in solution is relatively slow. So it means that you can't sort of change the mobile phase during a run because it just takes too long for the molecules to react to that change, and it just means that you broaden out the peaks because you've got these sort of how to explain this. Some of the molecules are still kind of behaving as if it's it's one sort of solvent mixture, whereas other molecules have started to sort of react to that change and behave as if they've got the new solvent mixture. So you end up with these sort of different populations of molecules behaving differently to each other, even though they're the same structure. And there's a range of different solvents that you can use to do normal phase HPLC. So normally, you'd have one of the solvents down at this end, so maybe hexane to dichloromethane. You would use that as the non-polar solvent and mix in a little bit of some of these other solvents down here, from tetrahydrofuran down to methanol. You wouldn't really use water as an eluting solvent. It's just going to stick strongly to the silica surface. But any of the others you've got the option to use those. And it's just showing the increase in the polarity of the solvents as you go down this list. Okay, so I'm making fairly good progress. So moving now on to the bonded phases. So this is relying on developing chemical synthesis methods which can be applied to these silica surfaces, so that we can replace the OH group that's attached to the silicon atoms with something else with different chemical properties. The initial attempts at doing this weren't terribly successful. So it's conceptually quite simple. Just think, okay, let's replace the hydrogen atom with something else. So this is analogous to ether compounds in organic chemistry. The chemistry is relatively straightforward. You can use an alcohol molecule, and that replaces the oxygen on the alcohol replaces the oxygen in the OH group, and you can have a range of different alkyl groups attached. There's R here, but these materials are relatively unstable. They can easily just get hydrolyzed, just reverse the process to get you back to the original silica. So alternative approaches were developed to make something which was a bit more stable, less easy to hydrolyze. And it starts off by replacing the OH with a chlorine atom, and then you can react that with nucleophilic reagents like organometallic compounds to form a silicon-carbon bond, or nitrogen atoms using an amine as the reagent to form a silicon-nitrogen bond. And these generate materials which are relatively stable, but the chemistry is quite messy and lots of byproducts and hard to scale up to a manufacturing scale. So these were abandoned, and an alternative technique was developed, which was much more efficient, cleaner process, better yields overall, giving a better coverage of the silica surface. And what it involves is using reagents where you're effectively adding another layer of silicon atoms around the surface of the particle. Using reagents where you've got a silicon atom attached to chlorine to promote the linking reaction, and a range of different alkyl groups attached to the silicon. It's mostly this kind of reagent where you've got one chlorine atom, 3 alkyl groups, and usually just 2 of those will be the smallest possible alkyl group, the CH3 methyl group, and a variable size group here, and what's happening during the reaction is that an oxygen atom on the surface of the silica replaces the chlorine, and you generate this additional silicon linkage, but the process stops there because the alkyl groups on that extra silicon are now unreactive. So it's quite an efficient way to cover the surface of the silica particles by modifying these OH groups. It's so some of the advantages of doing this are we're increasing the range of different properties that the stationary phase can have, so that we can efficiently add lots of different alkyl groups at the R position, because it's relatively easy to synthesize the initial reagent with a range of different modifications here, but it's the same fundamental process involved in then adding that to the silica once you've synthesized the chlorosilane reagent. We're helping to protect the silica now, so we're putting this coating around the surface, and we're protecting the silicon-oxygen network from hydrolysis processes, because if there's water getting into the system, the silica particles can slowly just dissolve in the water by hydrolysis of the silicon-oxygen chains. It does bring in an additional issue. If you're adding hydrocarbon chains, you can get slow oxidation of the hydrocarbons just from oxygen in the dissolved oxygen in the mobile phase. It can sort of cause free radical oxidation reactions, similar to what happens in lipid molecules in biological systems. There is an issue though, because these chlorosilane reagents, they are quite large molecules, quite bulky, and the silicon, the OH groups on the silica, they're quite closely packed together. So you can't, you don't necessarily get complete coverage of the silica with these reagents. So you end up with, I'll just kind of try and roughly illustrate this. So if you've got part of the surface of the silica particle, and we've got some of these silane groups, chlorosilane group reagents reacting. And you may get some OH groups, stuck in between them, and the reagents can't get in to react with those because they're getting blocked by the adjacent modifications. So you can end up with these OH groups still present, kind of buried underneath the bonded phase modification. And this can be problematic because you've got these little binding sites present, and if your sample molecules can sort of work their way through the hydrocarbon chains and interact with one of these OH groups, if they can form hydrogen bonds, for example, then suddenly they've got this very strong interaction with the stationary phase. And a certain proportion of your sample molecules may be able to do this, and that will dramatically slow down their evolution through the column. And that's going to be an example of the peak tailing that I talked about previously. Whereas some of the molecules end up much more strongly retained than the majority of the same type of molecule. So there's a couple of strategies we've developed to overcome this and try to cover up as many of these OH groups as possible. So I think it's reasonably well illustrated for the first example. It's referred to as end capping, and all you do is, once you've put in your main modification, you just do a second process where you put in the smallest possible chlorosilane reagent just with methyl groups present, and those reagents are small enough to sort of squeeze between the larger hydrocarbon chains and modify most of the remaining OH groups. It's a bit less obvious from this diagram what's happening with the polymeric bonded phases. I'll try and sort of give a rough illustration of what this leads to. But what you're doing is you start off with chlorosilane reagents which have got additional chlorine atoms attached. So that gives rise to multiple reaction sites on each silicon atom. So the first step, an oxygen atom on the silica replaces one of the chlorines, and you end up with this intermediate where we've added the extra silicon with the desired alkyl group R, but we've still got chlorines there, so it can react further. So we do another step, we replace the chlorine with OH groups, and we repeat the process. So we put in more chlorosilane reagent, so we're now forming these branched chains carrying the modification that we want, the R group. So what I'll sort of try and illustrate on the board is what the consequence of that is for what's appearing on the surface of the silica. So I'm not going to be very precise about this, just to give you an idea of what happens when you've got lots of branching of the silicon alkyl group chains occurring. So I'm not going to draw in the atoms or anything, but you're going to end up with this kind of process occurring. Yeah, this expanding network of chains or sort of branching out from one initial oxygen atom, and that we're not trying to modify all of the OH groups on the silica, but the ones which remain unmodified, there's such a dense network of hydrocarbon chains clustered around them that your sample molecules can't access them so easily. So these OH groups, they're there, but they're buried under so much hydrocarbon that they have a minimal effect on your sample molecule. So I've talked about just using hydrocarbon chains as the modification, and that's by far the most common type of modification in bonded phase HPLC. And that's the most common of all, the 18 carbon chain, the octadecyl group. But also quite common is having 8 carbons. So these would just generally be abbreviated as C18 HPLC, C18 silica, C8 silica, C4, just with a butyl group, occasionally used. And you can just use methyl group, the smallest possible hydrocarbon group. I don't think that's terribly common to use though. And having hydrocarbon chains on the surface, that's obviously giving you a non-polar surface. And despite that, you might think that means that just only non-polar compounds will interact with that, but quite a wide range of sample molecules will interact to some extent with this material. And
is that because of modifiers?
Not sure what you mean.
Like in the normal phase, there's modifiers like propanol 2 that are used.
Yeah, that's sort of different process here, because what we're thinking about here is a partition process where the sample molecules, they are sort of kind of semi-dissolving within the chains of the hydrocarbon. And there's a kind of, it's like a more obvious two-phase or sort of liquid-liquid partition process where the hydrocarbon layer on the silica acts like a thin layer of liquid. Then there's an interface with the polar mobile phase, and the molecules are sort of swapping across that interface. I'll sort of come back to that sort of partition process in a little bit more detail soon. You can also have different types of chemical structure attached to the silicon atom. So you could have benzene rings, such as phenyl, silica. But because we've got these carbon-carbon double bonds, or to be more precise, this aromatic ring structure here, because we're presenting different kinds of chemical bonds in this group, it can give you slightly different non-covalent interactions with the sample molecules. So it can change the selectivity for certain types of compound and give you different separation results. And the benzene rings are quite versatile. They can be modified using different types of chemistry. This would usually be before you add them to the silica, but you can introduce charged groups, like the sulfuric acid group, negatively charged, or quaternary ammonium groups, which are positively charged, so you can have ionic interactions occurring. You can have these styrene groups, so a benzene ring with an extra carbon-carbon double bond, and these can undergo free radical polymerization to give you a thin layer of polystyrene on the surface. So this, why would you want to do that? So polystyrene is a relatively soft material. So it doesn't coat so well with very high pressure elution. But if it's attached to a silica particle, then that's a much stronger, harder core material, and you can have this thin layer of polystyrene on the outside. So you have a particle which is behaving like polystyrene, but can cope with much higher pressures. It's not terribly common though. You can generate a surface which is polar, but with different kind of chemical structure to the original silica material. So you can introduce groups which have hydroxyl groups presented on the outside, or other polar groups like the cyano group or nitrile group, C triple bond N. And this allows you to do normal phase chromatography, but with groups which are with sort of modified polarity. So these OH groups attached to carbon won't be as polar as the OH groups on silica, and triple bonds will have sort of different polarity again, not hydrogen bond donors, for example. So you can do something like normal phase chromatography, but sort of varying the nature of the polar interactions which are occurring at the surface. Then you can have amine groups attached at the surface. Again, this can be involved in ion exchange chromatography, but it doesn't carry a permanent positive charge. It's going to depend on the pH, whether that's charged or not. And I've sort of found this comment in textbooks that they've been developed for carbohydrate separations, but it's never really been explained terribly clearly why. I've kind of speculated that it might involve particular hydrogen bonding networks with the OH groups and carbohydrates. Potentially also, though, I haven't found proof for this, but I'm just speculating here, but you may potentially get covalent, sort of reversible covalent bonding between certain carbohydrates and amine groups. I may be getting that completely wrong. It's probably more to do with particular hydrogen bonding arrangements. So that's probably a good place for a break. So what I'll be doing is discussing in a little bit more detail the most common bonded phases, which is the long hydrocarbon chains, which is referred to as reverse phase HPLC. So a 15-minute break, so just a little bit after 7:25 I'll resume. Resume, and yeah. So I'll say a little bit more about the reverse phase HPLC. So this is mostly using the C18 modification, and the practical consequence of having this non-polar stationary phase is that you need a polar mobile phase, so there's this contrast between them, and you can treat it as if it was like two liquid phases with the interface between them. So we're using water as one of the solvents, but it's usually mixed with a polar organic solvent, which will mix with the water. And most commonly it's methanol or acetonitrile, both reasonably unpleasant compounds, but they're not that volatile, so you can sort of get away with using them in the lab as long as you've got good ventilation. There was, I don't know, yeah, it's probably worth mentioning this. It's not been such a problem recently, but there was a period several years ago where the cost of acetonitrile really jumped quite dramatically, and lots of people were sort of desperately trying to redevelop all their methodology to use methanol instead. And it was like one of these situations where you have lots of coincidental economic problems. So it was kind of soon after the 2008 financial crash, and car manufacturing went down, and acetonitrile is a byproduct of manufacturing the upholstery in cars. So the volume of production went down. At the same time, I think it was 2 or 3 manufacturing plants in China had sort of big problems like fire or an explosion or something, so that shut it down. So the world supply of acetonitrile was suddenly very restricted, and so the cost shot up. Just kind of, I'm hopeless at economics and stuff like that, but it's just kind of interesting thing how all the stuff that we talk about, all the reagents and so on, there's sort of, you have to think about where they're coming from and what affects their cost and so on. That seems to have stabilised now though, so it's not quite so expensive. So, as you'd expect from the name, reverse phase HPLC, if you compare it to normal phase HPLC, if you take the same mixture of compounds, in almost all cases, the order that they elute will be the reverse of normal phase HPLC. So what this means is that with reverse phase HPLC, the less polar a molecule is, the longer it will take to come out, because it's able to interact more strongly with the non-polar stationary phase. So it can effectively dissolve more easily in that thin layer of hydrocarbon molecules. And you can, if you change the mobile phase, you can change the rate of elution, but in order to accelerate the elution, you need to reduce the polarity of the solvent. So that means increasing the amount of methanol or acetonitrile compared to water. So it's just a kind of snapshot of part of the surface of the C18 silica. So you've got these long hydrocarbon chains extending out from the surface, and you can, if you imagine that sort of extending to millions of hydrocarbon chains, you can start to visualize it as being like a thin layer of liquid, and you can have sample molecules are able to squeeze in between those hydrocarbon chains, and it's like they're dissolving in hydrocarbon solvent. So you can think about it as a partition process where the molecule. Yeah, let me try and sketch something out. So that's your stationary phase, that's the silica, the hydrocarbon layer, and then hydrocarbon chains that are all packed together quite densely, so that you get this, quite distinct interface between that and the water molecules mixed in with ethanol, of course. So there's a very clear interface between the hydrocarbon and the mobile phase. So you can imagine your sample molecules. Let's just take a simple something like that. You can imagine that. It can be dissolved in the mobile phase, but it can also go across that interface and be dissolved in that hydrocarbon layer as well. So mainly partition processes that we're using to model the behavior of sample molecules as they pass across this stationary phase. And what you can imagine is you're sort of having to think about this partition process as sort of continuous. So as the molecules go into the mobile phase, they move along the column a little bit, but then they can partition into the stationary phase, and they spend some time mobilized in the stationary phase for a while, and then they come back out into the mobile phase to move along a little bit further. And so you can sort of, you're trying to do a mathematical modeling of it, you need to think about this sort of constant equilibrium between the two phases occurring sort of continuously along the length of the column.
Is that modelled by this plate analogy?
Yeah, so that's kind of you can, if you want, you can sort of go into it in a bit more detail than I did in the theoretical lectures, and sort of do more precise modelling of what's happening, but using the same underlying concept of being a partition process with partition coefficients coming in. You could come up with estimated partition coefficients between the water and called octadecane C18 hydrocarbon to try and quantify a bit more precisely the behavior of the molecules. And because it's quite a sort of tightly packed layer, you can also think about it as having a non-polar surface at the interface, and you can think about adsorption processes, but that's less significant because it's only just van der Waals interactions which are that sort of process would be, that adsorption process would become more significant with modifications that have things like OH groups or C triple bond N groups, where you can introduce dipolar interactions or hydrogen bonding, etc. And it's just an illustration of some data to show the effect of changing the stationary phase or the mobile phase. So it's the same mixture of compounds that are being separated here, the same mobile phase in each case, but we're using different columns with different bonded phase materials. So at the top it's the C4 silica, in the middle C8, and at the bottom the C18. And it doesn't affect the most polar molecules, 1 and 2, that much, but all of the others you can sort of see a very clear increase in the retention time as you decrease the polarity of the stationary phase. What this slide is now showing is the effect of the precise manufacturing and packing process of the silica. So this is lots of different columns which are nominally the same. I think there's C8 bonded phase silica. The same mixture of three compounds, and what this is showing is the relative retention times for those three compounds on lots of different columns from different manufacturers. And I don't know what all of the precise differences between these is, but it's depending on exactly how they produce the silica, how they do, exactly how they set up the chlorosilane reactions, what additional steps like the end capping they might be doing. And you can see it's quite a range of different retention times there. I mean, there's no sort of absolute scale on this, but it's all sort of relative differences in the retention times. So yeah, you can see for this particular mixture, columns at the bottom are not very good. The ones at the top are much better and give a clearer separation. But for a different mixture of compounds, yeah, it would be a different pattern. So there will be particular applications where these ones at the bottom give you better separation than some of the others. So it becomes quite a trial and error process if you are trying to develop a method to analyze something which you want to use repeatedly. It's worth shopping around, trying different columns until you get the best mixture, or the best separation of that particular mixture. But if you are doing, this is sort of more of the case with the kind of research projects we'll be doing here. It's hard to, if you're doing lots of different types of samples, you're kind of stuck. You don't have the time and the funds to sort of shop around for the ideal column for each particular mixture. So you have to concentrate more on varying the mobile phase composition to try to optimize different separations. So reverse phase, although it's a little bit more expensive in terms of the stationary phase, the mobile phase is generally going to be a bit cheaper because it's mostly water that you're using. But it's become the standard technique, the default technique to use. It's much more versatile than normal phase. Above a certain polarity of your sample molecules, the retention times get sort of far too long to be useful. So it's really mostly useful for relatively non-polar molecules. Whereas reverse phase, this may be a bit counterintuitive. You can actually work with much more polar molecules more effectively because they're not retained so strongly that it takes too long for them to elute. As long as they can have some kind of interaction with the stationary phase, then you have the chance to get useful separation efficiencies. This partitioning process for the molecules to swap from this mobile phase to the stationary phase layer, that's a relatively quick process for them to swap between those two phases. So you can vary the mobile phase composition during the run, and the molecules will be able to adjust to those changed conditions quite quickly. So you're able to do that so-called gradient elution and get sort of nice sharp peaks coming out of the system. So that would normally mean increasing the concentration of the organic solvent relative to water. I mentioned this before, you're protecting the silica particles from hydrolysis, so that increases the lifetime of the column. And by using things like the end capping method, we're covering up the very highly polar OH groups on the silica. So we're reducing these issues of peak tailing, which occurs when the molecules interact very strongly with the silica surface. Okay, so because the mobile phase now it has water as a major component, we have to consider the pH of that mobile phase now. So pH doesn't mean anything with normal phase, because you're talking about organic solvents where there isn't this sort of dissociation occurring of the solvent molecules in the same way, and you don't have the protons sort of moving around within the solvent like you do in water. So, but with water we have to think about pH. Especially where we have analyte molecules which you're trying to separate, which are acidic or basic. So that generally means for acidic compounds that's going to be carboxylic acids that we're thinking about, and for basic compounds what we're talking about here is amines in almost all cases. When you get into if you're thinking about proteins, some of the side chains are slightly acidic that aren't as carboxylic acids, things like the phenol group on tyrosine, the SH groups on cysteine are slightly acidic, so you might need to think about those as well. But in almost all cases, it's carboxylic acids that are acidic and amines that are basic. So the reason this is important is that if these groups get ionized, they become charged. That makes them much more polar, and that dramatically reduces their interaction with the stationary phase, so it reduces their retention time. And if you get the pH wrong for these type of compounds, you end up with horribly broadened out peaks. So I mean, very early on in my career, when I think it was the first time I was really working with HPLC, I was trying to take a natural product, antibiotic, and modify it to attach amine groups. In fact, I want to sort of get back to doing this maybe in some of my MSc projects. And just to give an illustration of the problems that we had. So if we had the mobile phase at the wrong pH, we were getting chromatograms kind of like this. But if we adjusted the pH, suddenly this almost imperceptible kind of rise in the baseline sharpened up into a nice sort of proper HPLC peak.
What effect does that have on the area under the curve?
Oh, it's the same. It's just it's harder to measure it, and the peak absorbance is obviously much less, so it reduces the minimum amount that you can actually detect. So the reason this comes about, so if you're at the wrong pH, what that means is that the pH is close to the pKa value of the compound that you're trying to analyze. And at the pKa, if the pH equals that pKa value, what you have is a 50-50 mixture of the neutral and the ionized forms of the molecule. And they're constantly switching between neutral and ionized form. So what that means is as the molecule moves along the column, some of the time it's neutral and it can move fairly quickly. No, other way around, it's reverse phase. No. If it's neutral, it's moving relatively slowly because it can interact more strongly with the stationary phase. If it's ionized, it's interacting much less with the stationary phase, so it's moving more rapidly. So the molecules, they're sort of constantly accelerating, decelerating in their movement through the column, and some molecules are in the neutral form, some are in the ionized form, so they're all moving at different rates through the column, and that causes them to spread out and diffuse much more, giving you this very broad peaks. So what we want to do is to get all of the molecules into one state, either neutral or ionized, and keep them in that state as they pass through the column. So they're all behaving the same way and all moving almost at the same rate through the column. So you can do this in just a sort of just push the pH right to the low or high end by adding acid to the mobile phase. That gives you a low pH. What that means is that carboxylic acids will be neutralized at low pH, and so they'll have longer retention times. And so you can add things like acetic acids, formic acid, trifluoroacetic acid, which is a bit, reduces the pH a bit further. But if you want to increase the pH, so you do this maybe, that's what I was doing with my samples, because they had amine groups on them. We want to neutralize them, and so we added some base to the mobile phase. You can do this with ammonia, but you can also add things like triethylamine, which is what we were doing. That raises the pH and makes sure that amine groups on your sample molecules remain neutral. But you may have a situation where you want more careful control of the pH at an intermediate value. So you would use a buffer solution and control the composition of the buffer solution to fix the pH at a specific value. Like phosphate buffers can give you sort of controlled pH around neutral, but I can probably sort of vary it a little bit either side. But that does lead to potential problems. So if you look through the, if you think about the HPLC method that we're using for the practical class, that buffer solution contains phosphate salt. And phosphate salts are very good pH buffers. They're sort of allow very good control. I think they're quite, they hold the pH quite stable. But you can't use them if you're doing mass spectrometry detection, because the phosphate salts, when they get into the mass spectrometer, you vaporize the sample, the phosphate ions go into the mass spectrometer, but they can precipitate on the internal surfaces of the mass spectrometer, and that eventually sort of leads up to quite serious contamination of the instrument. It degrades the performance of the electrodes that are needed to keep mass spectrometry running. So it basically breaks your mass spec, and you have to open it up and clean out all of the salts. So if you're doing mass spec detection, you need to use different kind of buffer salts they're referred to as volatile salts, because they can decompose into small organic molecules that are easily vaporized and removed by the vacuum system. So it's things like ammonium acetate, which will decompose into ammonia and acetic acid, and they can be vaporized and taken out by the vacuum system. So you do need to think carefully, though, about the extremes of pH values because we're working with silica, which is fundamentally a water-soluble material, and although it's protected to a significant extent by the bonded phase layer, water can still sort of get through to the silica surface a little bit. And if the pH is very high or low, then protons, if it's acidic pH, or hydroxide ions, if it's alkaline pH, can also get in and start to cause hydrolysis reactions to occur within the silica. So it can weaken the stationary phase particles and slowly start to grow. So you can go down to about pH 2. You might be able to go a bit higher than pH 8, I think, but probably 10 would be the limit for that. So it's, you need to take care if you're sort of going to the extremes of pH, and maybe think about, maybe it's better to have your compounds in the ionized state, but maybe as a salt with something which is sort of relatively non-polar, rather than if you're separating out cations, instead of say chloride as the counter ion, maybe acetate with a bit of sort of organic structure to a little bit less polar. Okay, so I'm going to finish off. I don't think I've got time to sort of move on to the size exclusion chromatography. So I'll just sort of focus on explaining this idea of chiral HPLC quite carefully. So, have you all heard of chiral compounds? Anyone not? I want to briefly just remind you of the concept. So it's all to do with, it comes about from the fact that you're talking about organic compounds where based on carbon, and each carbon's got sort of 4 different groups attached to it. Each carbon's like a tetrahedral arrangement, and if those 4 groups are all different to each other, you can have 2 mirror image forms around that carbon, which are exactly, yes. They're fundamentally different molecules to each other. They have different 3-dimensional shapes. However, in certain circumstances, you can't tell the difference between them. So if they're in a symmetrical environment, like just in solution, where all the solvent molecules are just sort of moving around freely, you can't sort of tell the difference between those mirror image forms of the molecules. And that's what you would have in a standard bonded phase HPLC column. There's almost spherical silica particles coated with an even layer of the bonded phase material. These opposite so-called enantiomers, the mirror image forms, they're going to behave exactly the same as each other. They've got the same polarity, obviously the same molecular mass. They're going to undergo all of the same non-covalent interactions with the stationary phase and with the solvent, so they behave exactly the same as each other. But there's many applications where we need to distinguish them from each other, because, especially for biological applications, biomolecules almost always exist, if they are chiral, they almost always exist in just one mirror image form. Proteins, nucleic acids, they have this specific single enantiomeric form. So if we're trying to manufacture a drug molecule to interact with the protein or DNA target, ideally we want just one of those mirror image forms. There's famous examples of where it can be a problem with having the wrong enantiomer. You might have done had chemistry demonstrations with. This is not really a problem, but it's just an interesting feature. There's a terpene compound which is involved in giving scent of lemons. I can't remember what it's called. Limonene. That'd be limonene. It's got two enantiomeric forms, and one of them is what you get in lemons. The other one, I can't remember what it smells like. Some other slightly different citrusy smell. That's a sort of fairly benign example. But the most famous problematic one is thalidomide, where I think it's unstable. I think the two enantiomers, they can swap from one to another under certain solution conditions, and one of them is relatively okay. I think there's still considerable side effects, but the opposite enantiomer caused horrible birth defects. So so it's important to get it right, and there will be sort of less serious implications. Maybe the opposite enantiomer is not particularly harmful, but it's ineffective. So you're basically just wasting half of the material. Half of it's just useless. So this means that we want to develop manufacturing processes which produce just one enantiomer. But in terms of an analysis, we need to be able to check if we have the correct enantiomer from a process, and if there's a mixture, what are the relative proportions of the two enantiomers? So how do we achieve this? So one method, which doesn't involve changing the HPLC system, is to take your sample and do a chemical reaction on it. I'll try and I should have looked up a real example of this, but I'm just going to make something up here. An example of this. Actually, let me just take a picture of this before I write it out. Anybody recognise that molecule? It's ibuprofen. And it's got this carbon atom here, which I can't remember which way around the methyl groups are for the active form, but I'll just use the standard chemical notation. So like the methyl groups in this form's coming out, hydrogen's going back the way, and the opposite enantiomer will be like this. We swap the CH3 and the H around. And this, you can take this, compound like this, it's got a carboxylic acid group, we can turn that into an ester or an amide, and we could, for example, take this amine, I'm just making this up, I don't know if this is really practical or not. And form an amide bond. I'm not going to draw out the whole structure on the left, I'm just going to focus in on the bit, the chiral center. I'm just previewing some of the groups. Draw. So, the products that we formed, the chiral, so-called chiral center from the ibuprofen, we've got these two different orientations, and we have a chiral center on the amine that we reacted it with, but there's only one orientation of the methyl group and the hydrogen in that part of the molecule. So if you think about these two methyl groups, they're now oriented relative to each other differently in the two different products. This is what's referred to as diastereomers or diastereoisomers. And the way that they all sort of, sort of shapes that they will adopt will now be more distinguishable from each other, even in a symmetrical environment. So if you do this kind of modification, put it on a standard HPLC column, you'll now see two separate peaks coming. Before the modification, the two enantiomers would behave exactly the same as each other, and so would give a single peak. But that is obviously quite time-consuming. To take a sample, you have to then do a chemical reaction on it. You have to do some kind of extraction or washing step, maybe, before you put it on the HPLC column. And then you do the analysis. So there's quite a strong demand for HPLC columns, which can distinguish the enantiomers directly. But what we have to do then is to modify the surface of the stationary phase so that it carries groups which are themselves chiral, but exist as a single enantiomer. So what's going to happen is when the sample molecules interact with the stationary phase, they're not forming a covalent diastereoisomer, but they're forming non-covalent complexes, which are diastereoisomeric to each other. So there'll be a different combination of non-covalent interactions depending on the orientation of your sample molecule. I also try and illustrate that with the amino acid example. I've never done chiral HPLC myself. Or go on. You have?
Yeah, I use the chiral analysis using the SFC actually. I think it's called supercritical fluid chromatography.
Okay.
So we
I'm
have
not going to be covering that.
instrument which is having more than one column. It's depend on the compound. We use sometimes 4 column, 8 column, and I know one exceptional case where we used 12 column, which compound include more than 3 chiral carbon.
Okay, yeah.
Yeah, so
Can you
we have
remember?
some different states as well. So it's not a 2 isomers, it's a 3 or more than a 4 or 5. So the columns are separating all the compound at different level. And that
Okay.
I don't know how the instruments work, but it automatically separates the every compound in a different bucket.
Okay. Nice. Nice. What kind of, do you know what kind of modification was on the stationary phase?
I don't know. There's a similar column look like HPLC column, with a thick and very long, actually more than a like 2 feet long column.
Yeah. I mean, there may be likely to be other, examples of modifications, but I'll just pick out, a few that have been sort of
What's the
used for a long
modification
time.
used for like this example here? The reactor?
Well, that's not chiral HPLC column. That's,
No, but I mean for that reaction.
yeah, but that's, yeah,
It's just another question.
yeah.
Like, how did you create it? How did you create the diastereomers or aspirate?
Um,
Is that in there?
So, the kind of modifications that you're making to the HPLC column, all these examples, you're using biological materials because they are produced naturally in a single enantiomeric form. And an example of sort of picked out to discuss, they're based either on amino acids or on carbohydrates. So you can attach individual amino acids, and these are just named after the inventor. They're called, but you can also try to use peptides or proteins. They're not so effective. The idea is that you're sort of making a more complex structure for molecules to interact with. Cyclodextrins are common to those. They're based on carbohydrates. They're quite nice molecules. Quite useful for solubilizing drug molecules. And less effective is just to sort of think, rather than modifying a symmetrical stationary phase, start off with the stationary phase just being itself chiral. So that's where you have the stationary phase is actually made up of carbohydrates like cellulose. So just sort of dismiss the peptide protein modification straight away. They do give quite sort of complex binding sites, so you can get sort of quite a sort of distinct interaction with different enantiomers, but they're not terribly effective because they're easily saturated with binding of sample molecules, so you get overloaded and you get that peak tailing effect coming in. So just focus on just adding a single amino acid. So there's alpha amino acids like you get in proteins, where you have this chiral carbon, so alpha carbon between the amine group and the carboxylic acid group of the amino acid. This is not a proteinogenic amino acid that we're looking at here. I think they do come up in, that does appear in some antibiotics, but you'd probably be chemically synthesizing this. And we've got additional modifications, like we've got something attached to the amine of the amino acid to give extra binding sites for sample molecules. And you can have a couple of different variations on this. So, this is an application of putting amine group on the bonded phase, so that we can attach the amino acid to that amine, either a covalent amide bond, or it can just be attached by ionic interactions in this salt form. That will hold the amino acid quite tightly to the surface. So, think about the properties of the structural properties of the amino acid. There's various functional groups that can form non-covalent interactions. So we've got hydrogen bond donors, acceptors. There's non-polar regions for different sort of combinations of van der Waals interactions. The benzene rings I haven't really discussed this before, but between the benzene rings and other aromatic rings, you can get particular interactions between the pi bonding electrons around the ring. It's called pi-pi stacking interactions. So we've got lots of different possible binding interactions, but crucially they are in a specific three-dimensional orientation. So we now think about bringing in a sample molecule. So it's that's the reason I thought of ibuprofen as the example, I guess. But actually, it's not ibuprofen. It's been modified actually to put this extra group on. But this is not chiral. So the only chiral center actually was no, it's not ibuprofen. It's a variation on it. We've actually got a chiral center here. But it's this one that we're focusing on, and this is not the exclusive way that it can interact with the amino acid, but it kind of helps to illustrate the effect of switching the chirality. So, what I'm trying to illustrate here is that there is some kind of interaction between the benzene ring in the sample molecule and this benzene ring here on the amino acid on the stationary phase. So it's holding this part of the molecule like that, and we've got some hydrogen bonding occurring here between the amide groups on each molecule, and we've got the methyl group sort of poking out here in a particular orientation, sort of pointing away from the amino acid. But if we were to switch the orientation here, now just think that what we are trying to do is to keep that methyl group poking away from the surface. It's not sort of going to bind very strongly. It's just going to sort of bump into the stationary phase surface, and that would mean that the amide group was sort of flipped over to this position, pointing back the way, and that might potentially weaken hydrogen bonding, or it may mean that it could hydrogen bond to this amide group, and that might be stronger. But the key point is it's going to be different because it's a precise three-dimensional shape. It's going to, the way that the various different functional groups all sort of come together is going to be different for the two different enantiomers. So as they move through the column, they will be experiencing slightly different strengths of interaction with the stationary phase. So one of them will move more slowly, the one that binds more strongly. So just finish off with the cyclodextrins. I think these are quite interesting molecules in themselves. The byproducts of cellulose production, I think, in nature. I don't know if they have any kind of biological function of their own, or whether it's just an accidental process of the enzymes which are making cellulose. Anyway, the long chains of carbohydrate groups in cellulose, they can sort of, if it sort of wraps around and you have a sort of short chain and it sort of wraps around and sort of joins one end to the other, you get these ring type structures made up of 6, 7, or 8 glucose monomers. And they form sort of quite rigid structures basically with a hole in the middle. And depending on the number of glucose units, the hole has different sizes, sort of illustrated here. Generally, the most useful one is beta-cyclodextrin. The hole in alpha-cyclodextrin is too small for most molecules to fit into, but lots of small molecules can fit neatly into the beta-cyclodextrin. Gamma-cyclodextrin, it's a bit bigger, but it's a little bit more flexible, and so it kind of folds up a little bit more. So the optimum properties come with beta-cyclodextrin. It's got a kind of rotational symmetry around the ring, but it is chiral. So all of the OH groups around the edge of the molecule, they are pointing in specific three-dimensional orientations. So the idea with this is that you can have the cyclodextrin attached to the stationary phase. Making use of the fact that there's lots of OH groups on the cyclodextrin that you can do chemical reactions with. And then you have a sample molecule which has some kind of, oh, sorry, I forgot to mention something. So if you just at first glance look at the cyclodextrin molecule, and you might think it's very polar, lots of OH groups, but the way that it folds up into its three-dimensional structure, the hydroxyl groups are mostly pointing out the way so that it dissolves easily in water, and there's lots of CH bonds as well. They're not sort of drawn out in here in this diagram, but they are there, and those CH bonds are kind of more sort of pointing in the way, or what it leads to is that the interior surface is a bit less polar, and non-polar molecules, if they're small enough, they can fit inside that cavity and experience more in the way of van der Waals interactions to hold them in there than the polar interactions. So it's quite useful sometimes as a solubilizing agent. So you can get relatively non-polar molecules, you can get them into aqueous solution if you mix in some of this cyclodextrin, because they can spend most of their time sitting inside that hydrophobic cavity. But if there is a chiral center attached to that, the part of the molecule which sort of fits into the cavity, then keep in mind that you've got an array of hydroxyl groups and they're pointing in specific orientations. That chiral center will interact differently with that ring of OH groups depending on the orientation of the groups. So if you swap, let's say groups Z and Y in position, they are now going to experience different interactions with that array of OH groups on the cyclodextrin. It's kind of conceptually quite a nice design, but it's not quite as good as the amino acids. It's I think just potentially can be saturated more easily with a certain concentration of the sample. Eventually you're going to sort of fill up all of the cyclodextrin molecules. And the cyclodextrins are relatively large, so you can't pack so many of them onto the silica surface as you can with the amino acids. And yeah, I think that's all I'm going to have time for today. So I get a break now, and then it's 5 sessions on mass spectrometry, and then I'll come back to deal with other analytical methods. I need to get to grips with the electrophoresis content that previously taught by someone else, but I'll also talk a little bit about the size exclusion and ion exchange chromatography as well.
And what will we should expect coursework for the next 5 weeks?
Yeah, I was going to do sort of 1 or 2 exercises on mass spectrometry.
It's not 5 weeks, it's
5 sessions, yeah.